Okay, here we're going to continue on unit 1, lesson 2, and the lesson here it is chemical bonding. So electrons bound, so the atoms bound. Why they bound? So why they bound? Okay, so atoms bound to be stable. Why do you want to be stable? Because it is the rule. Atoms lose or gain electrons to achieve the stability. They want to be stable. The stability of a noble gas, of a noble stability of a noble gas, not with Z, with S, because it is not French. Noble gas, a noble gas electronic configuration. So atoms, for example, chlorine say, I'm not stable. I'm not like a noble gas. I'm not stable. So I have to go and be like a noble gas. What are noble gas? What are the atoms that are stable? Look to the periodic table. Which atoms are noble gases? These guys here. They are the stars of the periodic table. Stars, everybody wants to be like a star. It is the stars of the periodic table. Helium, neon, argon, krypton, xenon, and etc. This is the stars. They are stable. They don't react. Why they don't react? Because they are stable. They don't need anything else. And they are stable because they have 8 electrons in their outer shell, or in their in their outer shell, or in the that's it. Okay. So for example, say I have lithium. Lithium can say, I'm not stable. Why? Because I'm not a noble gas. I'm not a star. So I have to do something to be like to have the electronic configuration of a noble star. Which one? It will try to be like helium. Why? Because helium has 2 electrons. Lithium has 3. Lithium can't be like neon, because neon has 10. So he has to catch 7 electrons. It is too hard. But he can say, I'm going to lose 1. If I lose 1, I'm going to be like helium. That's why lithium plus is stable. That, for example, it is very difficult to find lithium. Lithium in nature, you're not going to find it. But you are going to find lithium plus. Lithium will give its electrons to another one. That's where it will bind. The same, for example, magnesium. The magnesium has how many electrons? Has 12 electrons. Magnesium says, I'm not stable because I'm not a noble gas. So I'm going to try to be like what? I have choice to be like neon with 10 electrons, or argon with 18. With 18, I have to catch 6 electrons. 6 electrons is too hard to have. So I'm going to be like neon by losing 2 electrons. That's why in nature we're going to find Mg2 plus, mix it with other. That's why we have, for example, factories. If we want to have magnesium, we have to do work to give 2 electrons and force magnesium to have the 2 electrons, and we have to forbid him to have any contact with other one, because magnesium will give his electrons at the first opportunity. He will give its electrons. That's it. That's why metals try to lose electrons, because for them losing electrons will be easier to be like a noble gas. There is exceptions, of course. Now, if we see chlorine, for example, chlorine, it's another story. Chlorine has how many? 17 electrons. But you can say, if I have 1 more, I will be like argon. That's why chlorine try to gain electron. That's why, for example, chlorine will have Cl- that we are going to find in nature. Okay, if it's found. That's why, for example, we have NaCl. NaCl, the sodium wants to lose electron. Chlorine will to gain 1. So that's why we're going to have ionic bonding. So you understand the picture. Non-metals will try to gain electrons because they are close to noble gases. Metals, they are far from noble gases. They want to to gain electrons. This is what we call the octet rule. So I'm going to write it here, the octet rule. This is what I stated. It is the octet rule. Why the octet rule? Because the noble gases has 8 electrons except the helium in its outer shell. Okay, so the stability, the octet rule, the octet rule. Atoms try to have 8 electrons in their outer shell or a valence shell, outer shell, except helium. When they want to try to be like helium, yeah, there is exception, except helium, who has only 2 electrons in its outer shell and it is stable. This is what we call it. So everybody will apply the rule. I can't be like helium, so I have to have 8 electrons. Okay, so an atom is most stable when it can obtain a noble gas electron configuration in its outer orbitals. The outer orbitals are collectively called the valence orbitals. So the outer orbitals, we call them valence orbitals. But you know them already because it is grade 10 and grade 11, grade 9 even. Valence electrons. And the electrons are called valence electrons on the shell, valence electrons, the most, yeah. Typically, the valence orbitals in an atom are the outermost s and d orbitals. These orbitals get involved in the bonding process with other atoms. Yeah, this is the rule. This is what we said. Now, how physically the bonding take place? By overlapping. So I'm going to write orbital overlap diagram. Orbital overlap. Orbital, yeah. So orbital overlap diagram. Remember, now we can't follow the electrons. We said that electrons, we can't follow the electrons, but we can follow where they can. We can follow the orbitals. So, for example, I'm going to, first I'm going to start by bounding representation. Bounding representation. For example, I have a hydrogen. It has one S that will bound with another hydrogen. I'm going to put it also here, plus another hydrogen, plus here. It will give me HH. But how the orbitals will work? The orbitals, they will overlap. Like that. I have the first hydrogen and I have the second hydrogen. This one, I want S. And I will have this one here. So what they will do, they will mix their orbitals. 1s, 1s, they will, this is 1s and this is 1s, and they will mix them. Remember, 1s, we said it is a room. So what they will do, if there are, for example, one room and another room here, they will break only the wall and they will make the 2 rooms. If you want, you can look at that. But in chemistry, we represent the bounding by an overlap diagram. So now I'm going to represent the overlap. Can I erase? Yeah, I'm going to erase. Overlap diagram. 2 overlap diagram. Overlap diagram. So how the overlapping works? I'm going to show you how this works. For the hydrogen, overlap diagram, hydrogen. How we represent that? The hydrogen has one S. We put hydrogen here, and we put the electrons that will react, only the electrons, the outer shell that reacts. So this one is 1s, this one is 1s, and we put a box like that. This is how chemists represent the bonding when we use the orbitals. So this is the representation. So you have, this is your answer like that. Now I'm going to take another example, oxygen, for example. I'm going to this one we did it, H2. Now I'm going to make an overlap diagram for H2O. H2O, I will have an O here, an H, and H. And what will represent only the outer shell. For the hydrogen, what is its representation? What is the configuration? It is 1s1. For the oxygen, remember, it is 1s2, 2s2, 2p4. So which ones will react? Only the outer shell, not the inner shell. It is the 2. 1, 2. The 2, it is the outer shell. So we're going to represent only the outer shell. And we're going to represent them like that. This is 2s. I'm going to represent it with another color. This is 2s. And this is 2p. And the p, it has how many? It has 3. Remember, p has 3 rhombus. S have only 1. And we know that we have 1 electron up, 1 down, 1 up, 1 down for oxygen, 1 up, 1 up. Now the hydrogen, it will react. It will react with what? With 1s. So I'm going to put the electrons that will react with another color. Going to put this color here in blue. So for this hydrogen, I will have this electron 1. Okay, I'm going to put 1s here. And for this hydrogen here, its electron will react with this one. I'm going to put it here, 1s. And what we're going to do, put the boxes. I'm going to put a box here with the electrons that react, and I'm going to put the box here. I'm going to redo. I'm going to take this one. Okay, so because it was not well done. Okay. Like that. So this is the overlap diagram for the bonding of hydrogen, of oxygen. In the end, what we have an O with an H and with an H. This is the representation overlap diagram. So if you have a question about, if I give you a question about overlap diagram, this is what I want you to give. You have to give, this is the examples. Here I'm going to stop now because this is, and we're going to see later. Okay, good. Bye.